Hi all, I am Adnan Ali. I'm from the group Deep Thinkers. Today, I will present our assignment on state space representation for two-player games. We are using tic-tac-toe as a running example for this. So we will be first outlining the problem and the formal state space model. Then we will explain the search algorithms that we used, which are IDFS and A-star. Then we will walk through our implementation and finally compare the performances and discuss the lessons that we learned. So introducing our team members, me myself, Adnan Ali, Gogul Krishna MR, Ajmal K, and Chris Charles. Going forward, this is our problem statement. Tic-tac-toe is a two-player game played on a 3x3 grid. As I said earlier, we are using tic-tac-toe as a reference, as an example here. Player X and player O take turns making empty cells. The first player to place all the three marks in a horizontal, vertical, or diagonal line will win the game. And it will be ending in a draw if all the 9 cells are filled and no player has all the three same entries in a row. The following actions are permissible. Those are uh, we can place an X in an empty cell, means if X belongs to us, if I am the player using the X, so I can place X in any empty cell and place an O in any empty cell. Check if the move results in a win, draw, or continuation. The task is to determine a sequence of moves that will result in a win for one player or a draw if no winning sequence exists, ensuring fair play between both players. Going forward, state space representation of the two-player game. The states can be represented as each state is represented as a 3x3 grid where each cell can be X marked by player X, O which is marked by player O, can also be an empty cell, and as we know all the empty cells will be filled as the game progresses. All the empty cells will be filled by either X or O. Initial state is all 9 cells will be empty, and our goal state, the winning state, any state where a player X or O has three marks in a row, either horizontal, vertical, or diagonal, is allowed. Or it will be a draw state, which means there will be no specific winner in the game. All cells are filled and there is no winner we can find, so we can declare the game ended in a draw. And the operators is like place X in any empty cell, place O in an empty cell. After each move, check for win, draw, or continuation, as we discussed earlier. This is the state space diagram. It's impossible to represent all of the possible states in a single frame. So this is just a subset of all the states. We can see there's about 9 different states possible in the first depth itself. So this is just the subset of how our entire state space diagram might look like. Going forward, algorithms used. This is the most highlighted portion of this presentation. Iterative deepening DFS. Explores game states using depth limited DFS repeatedly. Combines the space efficiency of DFS with the completeness of BFS. That's the highlight of this algorithm. It's space efficient, and also completeness of BFS is also a feature of this algorithm. Useful for exploring the tic-tac-toe game tree within limited depth. So the solution that we get using this algorithm will be uh, within limited depth, which means we will not have to be the method will be optimum. The solution we get using this algorithm will be an optimum method. And A-star search going to A-star algorithm uses a heuristic to guide the search towards winning states. Example heuristic can be number of moves required to win or block the opponent. So a heuristic is something that can guide the algorithm, that can guide the method of search to make it easier and fast, and guarantees optimal play when using an admissible heuristic. Going to the code explanation, we can see the first portion, that's the important code part. As we can see, creates an empty 3x3 tic-tac-toe grid, and each of the 9 cells is marked as empty initially. starts iterative deepening on the empty board. The search will explore possible moves up to 6 levels deep. Player X makes the first move, returns the first terminal state. And this is the entire code of DFS function. Explores all possible moves up to a certain depth in the tic-tac-toe game. The parameters: board, current state of the game, depth, current depth of recursion, limit is maximum depth to explore. Player can be the current player X or O, either X or O. The logic is, considering the base case, if the maximum depth is reached or the game is over, which means the function is terminal with the parameter board, return the board. Otherwise, determine the next player for the upcoming move, loop through all the empty cells, simulate a move by the current player, call DFS recursively with the new board, increases depth and next player. If the resulting board is a terminal state, that's a win or a draw, which is the goal state or something, return it immediately. If no terminal state is found within the depth limit, which means if we reach the depth limit and no one is the winner, which means return the current board itself. Iterative deepening DFS function. The function purpose combines the depth limited search with incremental depth. Increase to ensure finding a terminal state efficiently. Parameters: board, current state of the game. Max depth, maximum depth to explore. Same as we seen before. Player, starting player, it's X by default. We assume the player X is starting all the time. Logic: start with depth limit equal to 1 and increase iteratively up to a maximum depth. Call DFS for the current depth limit. If DFS finds a terminal state, that is win or draw, return that board immediately. Or there is no winner, we will return the current board, which means in the case of draws, we will return the current board. This is the code for the A-star algorithm. There's a heuristic defined above and the A-star algorithm is defined below. Going to the explanation, the heuristic function purpose is assigns a value to a board state to indicate how favorable it is. Which means there's a weightage, there's a value to each state depending upon the closeness of that state into the goal state. It depicts the chance of finding the goal state earlier with optimal solution. The logic is, if X wins, score plus 10, if 0 wins, score is minus 10. Otherwise, which means a draw or unfinished state without getting to the goal state, score will be 0. Key idea is guides the A-star algorithm. A-star search to prioritize moves that are more likely to lead to a win. This is the entire explanation of the A-star function. A-star algorithm finds the optimal move sequence in tic-tac-toe using a heuristic guided search. We have seen the heuristic before. Parameters: board and players are there. Board, current state of the game. Player, current player, X by default, as we said earlier. Logic: initialize priority queue with the starting board and player. Each item stores F score, board, player. Loop until queue is empty. In that loop, inside the loop, pop the board with the lowest F score. That's the first one. If it is a terminal state, we'll return it. Generate all possible next moves using generate moves. For each move, G is the cost of making a move. H is the heuristic value of the new board. And F is the sum of G and H. Total score used to prioritize moves. We will be determining our moves based on the F score, which is the total score. And we have push. That push into the priority queue. Here is the performance analysis of our algorithms. We can see the time taken in seconds for IDFS and A-star algorithm. We can see the nodes expanded. We can see the length of the path visited. So going to the observation efficiency. Time and nodes expanded. A-star wins here. A-star exhibits dramatically superior efficiency, solving the problem nearly 83 times faster by expanding 541 times fewer nodes. We can see that here. The observation slide is the interpretation of this performance analysis. This is in terms of numbers. This is in terms of the inference we get from these numbers. This advantage stems from A-star's use of a heuristic function which effectively guides the search and prunes unproductive branches. Talking about the optimality, IDFS is winning here. which means it found a path of length 5 while A star found a path of length 7. Assuming the path length corresponds to the cost, this suggests that the heuristic function used by A star was inadmissible, overestimated the cost to the goal, or the cost function was not uniform, leading to a suboptimal solution. IDFS guaranteed to find the shortest path in terms of depth or steps. That's why in optimality IDFS is winning. Saying about the conclusion, for speed and state space exploration efficiency, in that case, A star is the clear winner. It means it highlights the power of informed research. For guaranteed shortest path or for the guaranteed optimal solution, IDFS algorithm proved better in this specific run. A star results suggest a need to verify the admissibility and consistency of the heuristic as we expect it to happen that way. So thank you. That's all about the presentation we have. And we would like to invite questions if anyone have any doubts. So thank you so much.